Where's the rest? On the way. Is sodium on the way? Okay. Oh, people are think. Is Eddie okay already? Or not? Okay. Okay, maybe we just start the recording. Don't want to waste more time. So let's check some terminology on polynomial ring or ring in general. Let's look at polynomial ring first. Okay, so last time Eating talked about a degree. So degree, when we talk about degree, we need to mention degree of what? Okay, so what's the degree we have looked at? So we have looked at the degree of a polynomial. Okay, how do we define the degree of a polynomial? This polynomial called Px is what? How do you define degree of a polynomial? Yeah, check. Sorry. The highest exponential of x. Okay, so what do we call that? What do we call that? What do we call that? That term in our polynomial. So polynomial consists of what? Polynomial consists of what? What do you call the term in polynomial? Sorry? Leading terms. Okay, leading terms, sure. But in the polynomial, there are linear combination of what? Polynomial are linear combination of what? Yeah, the power of x, right? Okay, so those are called the monomial. Okay, monomial. Right. Okay, so they are called monomial. Okay. So the degree of the polynomial px is the largest integer h s such that the coefficient of the monomial x to the s is non-zero. Okay, the largest one. Right. So for example, what's the degree of 4 plus x squared plus 3x cubed? What's the degree of this polynomial? What's the degree of this polynomial here? Right. Here the degree is 3 because the highest integer such that the coefficient is non-zero is 3. Okay, so this is true. Right. So last time we didn't define the degree of a monomial. What's the degree of a monomial? Si, for example. Okay, the degree of a monomial is of xi is just I is the power I, or is the power I. Okay, okay, no? Which is I. The degree of a monomial is just I. It also makes sense to just apply the previous example, right? Previous definition. You see xi as one monomial, and there's only one monomial there, right? Then there is the largest already. But yeah, it's the largest. And then the power of the monomial is exactly the power of the monomial. Okay, what did I say? The power of the monomials is the exponential, right? It's the power. Okay. 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 Yeah. Then last time we defined the leading term, leading coefficient. So what's the leading coefficient of a polynomial? So the leading coefficient of a polynomial, so this is leading, right? So how it leads? So you look at the coefficient of the highest degree monomial in the polynomial. Okay. So for example, what's the leading coefficient of 4 plus x squared plus 4x squared? So what's the leading coefficient here? So you look for the highest degree monomial. Okay, and then you look at what's the coefficient. So what's the coefficient here, Brandon? 4. Okay, so it's 4. Leading coefficient. But you can see that in when we look at the ring, polynomial ring with coefficient in ring in R, okay, we always look for monic polynomial. So what's a monic polynomial? More, MO mean mono. Mono mean once. Okay. So what's one? Where is the one? The monic polynomial is a polynomial with leading coefficient 1. So for example, x plus x squared is a monic polynomial. Okay. But a non-example is x plus 2x squared is not a monic polynomial. Okay. Because the first one, the leading coefficient is 1, but the second one, the leading coefficient is 2, which is not 1. Okay, make sense? Okay, so why we look for this monic polynomial? Because remember that we can do division with remainder, or we can do the long division in polynomial. Right? Okay, we need a monic condition here. Because not every element in ring is multiplicatively invertible. Okay, so you cannot always divide by any non-monic polynomial. You must divide with monic polynomial. So I'll say that a monic polynomial plays a crucial role in division with remainder, the polynomial ring. Okay, polynomial ring. Okay, make sense? Okay. You can only always divide by a monic polynomial. If it's not monic, then you cannot divide. But if you work in a polynomial ring with the coefficient in field, then you can, because every coefficient is multiplicatively invertible. Okay? You can always make the monic into coefficient 1 by just multiplying by some element in the field. Okay? So far, okay? Okay, let's continue. So we've talked about polynomial ring. Let's return to the ideal. Okay, last time we stopped at ideal, right? 理想. What's this ideal here? Okay, so what's the definition of ideal? An ideal is what? Don't recall what an ideal is. An ideal is what? Where do we get the ideal from? From a ring, huh? Right. Okay, it's a non-empty subset of R. So what's the R? We need to define R. Ring, right? Of a ring R. Such that it is closed under addition. Second, you need to close under multiplication, right? Not just multiplication within the ideal. It closes under multiplication with the elements that is outside the ideal, inside the whole ring. Okay, so let me write it out. So there are two properties here. Okay, first, close under addition. So how is it closed under addition? Let's give a name to this idea, right? Okay, let's call it I idea. Okay, then for all st in I, right? X plus t must be in I. Okay, closed under addition. Second, it is closed by closed under addition. Closed under multiplication. Okay, multiplication by elements in R. Okay, so meaning if you take any elements in your ring, okay, and then any elements in your ideal, okay, then R times X is still in the ideal. Yeah. Okay. Okay, so this second condition is really strong. Okay, you can take any element in your ring, okay, and then multiply with the element in I. You will stay in I again. Okay. All right. So we'll define a specific definition here. So in any ring R, okay, the multiples of an element A, let's call it A, form an ideal. Okay, so this is a very important ideal that we call the principal ideal. Okay, principal ideal. Okay, it is generated by A, and we will denote it by sometimes we write bracket A or round bracket or square bracket, right? Sometimes also we will write AR or just RN because our ring is commutative. So what is this set here? So this set here is just R times A for all R in R. So you take an element A, okay, and multiply with any ring element, okay, and then this constitute a set. And then we say that this is an ideal. Can you prove that? Is this an ideal or not? Is this an ideal or not? Try and prove that this is an ideal. Is it, first of all, is this a non-empty subset of the ring? Why is it not empty? What must be in there? Huh? A must be in there, right? Because your ring have an identity. Okay, so first of all, this set is non-empty because 1 times A is in there, right, which is equals to A. Okay, and then is this a subset of ring or not? Why is it a subset of a ring? All these elements are just R times A. So they are both elements in ring. And ring is closed under multiplication. Okay. So this set is a subset of R because ring is closed under multiplication. Okay. Okay. And then what else you need to check? So check. What else do you need to check for ideal? So check. What else do you need to check for an ideal? Close under addition. Right. So you need to take any two elements in the set. Okay. Take x, y in A, right? So we want to show that x plus y is in A again. Again, the idea of A. But what is x now? What is A? What is y? X and y are what? What's the form of x and y? Yeah, what's the form of x and y? You are multiple of A. Okay, you are a multiple of A. So meaning what? So there exists R1, R2, such that x equals to R1A and y equals to R2A. Right, because I'm taking element from the set that looks like all the elements looks like RA. Make sense? Okay. And then what? Then I want to show that this element is again R times something. Some R times A. Can I do that or not? What do I do? I can use distributivity, okay, in my ring. I can distribute my ring element, right, by distributivity in R. Is R1 plus R2 another R1? Right, because our ring is closed under addition. It's a group under addition. Okay, so we can choose R3 equals to R1 plus R2 so that x plus y is in, again, in the principal ideal generated by. Make sense? Does it make sense? Question? If you're confused, please ask, because there's nothing special here. Please ask. Don't be shy. Okay? Can follow? Okay, so it is closed under addition. How about closed under multiplication? So take any x in my principal ideal, right? And then take any r in my ring, okay? Then we want to show that r times x is still in A, okay? R times x is still in A. But what is r times x? R times x is equal to r times r1 times A, okay? For some r1, such that x equals to r1A, right? But what can I do? I can use associativity. Okay, I can use associativity. By associativity in R, I can write as R1 times R1 times A. Okay, but again, R is closed under multiplication. Okay, so we can choose R2 equals to R1 R times R1 such that so that Rx is in the principal ideal. Okay, makes sense? This principal ideal is very important, and we will be using this principal ideal a lot. Okay, in different ring, we will be looking at this principal ideal. So you can think of this as a cyclic subgroup in the group sense. Right, cyclic subgroup generated by one element. Here, ideal is also generated by one element. Okay or not? But you can see that this principal ideal has more. Of course, it has more structure because it's an element in ring, but it is more than close within itself. Okay, you can take outside element and then multiply with the element inside, but you still stay inside. Right? Any element you take from the ring, you multiply with the element inside your ideal, you still stay inside your ideal. Okay. Previously, we just close within the set, but now you take the outsider. Right? You take the outsider, you join with yourself within the set, but you still stay inside the set. So this is an ideal. Yes. What do you mean? Oh, I mean, to show that something is in this set, what do you need to show? You need to be able to write into a form of R times A. You need to write into a form of elements in ring times A. But here is RR1 times A. So how do you make sure RR1 is an element in the ring? How do you make sure the elements RR1 is in the ring? Make sure that R times R1 is in the ring. Right? How to make sure R times R1 is in the ring? Because R is R, let R2 be R times R1. Yeah. Yes, then you can make into a form of R times A. Make sense or not? Make sense? Okay, yeah. Right. Because all your elements have to be in R times A form. Okay, so you need to make sure it is some element in R times A. Okay, so this is what you need to do. Okay or not? Is that okay? Make sense? Other question? This is very basic question because anything how to show about ideal is using the same way. Just that you need to understand the definition of your set. Okay? Can proceed? More question? Okay, let's continue. So there's a proposition here. So actually we can realize a ring, okay, as a principal ideal. Okay, you can realize the ring as a principal ideal. So what's the principal ideal do you think? How to generate a whole ring? Yeah, using one element. You just use one, right? Because R times one, you get back your R. Okay, so you just use one to generate everything. Correct or not? Right. So you go back to here, and then you put a one here. What do you get? Everything here is R times one. So you get back your R. R is from the ring. Okay, any R in the ring. So you will generate the ring. So this is called a unique ideal. Okay, unique ideal. So whenever you found one in your ring, in your ideal, you actually generate your whole ring. Because from one here, you can get everything in R already. Make sense or not? So whenever you see one, you found one in your ideal, that means the ideal will generate the whole ring. Because you can take every R, multiply with one. Then this thing, since it is an ideal, is still staying my ideal. And I can get everything in my ring. Okay, using the one here. The next important, you can try and prove this. Okay, this is very easy exercise to do. Next, the set consisting of just zero element, okay, just zero, is the principal ideal zero. Okay, this is what we call the zero ideal. Okay, zero ideal. Okay. So you can imagine that if I take any element in R, multiply by zero, what do I get? I still get zero. Okay, and then prove that this form an ideal. And then there's just zero inside your ideal. So you can try and prove it. And next, an ideal, okay? An ideal is proper if it is neither the zero ideal nor the unique ideal, okay? So we'll call an ideal if it is an ideal in between these two. We don't want to get a whole ring. We don't want to get a trivial ring, okay? A zero ring. Okay, we want something non-trivial between these two. Okay, then we call it a proper ideal. Okay, so for now you should be observed that an ideal actually is almost a ring. Okay, it's almost a ring. You can check all the ring axiom, but except one. Okay, except the unique ideal one, unique element one might not be in I. Okay, might not be in I. One might not be inside them. Okay, because if one inside there means what? You will get the whole ring. Okay, you will just get the whole ring. So one might not be in there. Okay, unless what? Almost impossible one is in there, because if one is in there, you just look at the whole ring. So unless I equals to R, it will not be what we call a subring. Okay, so an ideal is almost not a ring. Always is always not. Almost always is not a ring. If it's a ring, then you must contain one. If you contain one in your ideal, you will get back the whole ring. Yeah. So ideal is a very special existence. Okay, it's a very special existence. So let's look at some example of ideal. So for example, let's look at the morphism here. What's this morphism? We want to fix R under this map here. And then to tell you a morphism from a polynomial to R, what do I need to tell you? I just need to tell you how the x go. Okay. Once I know where x go, and then I also need to know how the coefficient go, right? Okay. But I say I fix R. So meaning all the R goes to R. Okay. So for example, under this map, 2x here will move to 2 times 2. Okay. Makes sense? Okay, I just tell you where the generators go, and then it will extend naturally, okay, using homomorphism property. Anyone want to guess what's the kernel of this map here? What's the element that gets sent to 0? And what's the polynomial that gets sent to 0? Want to guess? Of course, 0 is always in the kernel, right? 0 always gets sent to 0. Right, this is a property of group homomorphism. You need to set 0, right? Constant function, does constant function send to 0 now? Constant function all sends to itself, right? I fix the coefficient R. Okay. Which elements get sent to 0 here? Which element gets sent to 0? Try and think. Yes, x minus 2. Right. Because what is x minus 2 goes to? 2 minus 2, which is 0. Okay, x minus 2. Okay. And then what else goes to 0? Ax minus 2a, what is that? Ax, what is a? Or ax minus 2a, okay. So meaning you take let's take anything in your polynomial ring, okay? You just multiply to x minus a. What do you always get? You always get applies to the m and then multiply by 0. You always get 0. Okay? Make sense or not? Does it make sense? I don't care what m happen, but I know that I'm multiplying with a factor 0. And then this one, this form an ideal. Okay, so this form an ideal. So the kernel. So my claim is the kernel of phi is generated by the polynomial x minus a, x minus 2. Okay. Okay. So what's this definition here? This is a principal ideal generated by x minus a. So what's the element in here? All the multiple of x minus 2. Okay, so let me write down this definition to recall for you what's the principal ideal. So these are all the things that you take your R, multiply x minus 2, where your R is in the ring. So my ring here is the polynomial ring. Make sense? Okay. Make sense? So this is my claim. Okay, this is my claim. How to prove it? How to prove this? So this is equality, right? Equality of set. So you need to show two subset inclusion here, left to right, and then right to left. Okay. So you need to show that kernel V is a subset of the principal ideal, and then the principal ideal is a subset of kernel phi. Okay. Which one is easier? Which side is easier? Going from the X, the principal ideal, to the kernel, right? This side is easy. Why is it easy? You just take phi, apply on any elements R times X minus 2. What do you get? You get phi R times phi X minus 2. But phi X minus 2 is just 0. So this means that for all R in the polynomial ring, phi of R times X minus 2 is equals to 0. So it's in the kernel. Okay. So R times X minus 2 is yes. Okay. But how about the other direction? Okay, how to show the other direction? You take any element in the kernel of V. You want to show that it is in the principal ideal of X minus 2. Okay. How to show this? Take any polynomial in P. Okay, let's call it PX. Okay, take any polynomial here. Okay, we want to show that it's in the principal ideal generated by S minus N. How do you do that? If you want to show that this is in the principal ideal, meaning what? This polynomial have to be written as a multiple of X minus 2 without remainder. The remainder is 0. Make sense or not? Correct. Or not? You want to write Px as a multiple of X minus 2, meaning X minus 2 have to divide Px without remainder. Make sense? Okay. So, what can we do? We can use division with remainder. Okay. In the polynomial ring, Rx. Can we use or not? Can we use that or not? Can we use this to divide Px with remainder? So we will get something like Qx times X minus 2 plus Rx for some polynomial Q and R. Can we do it? Can we write this or not? Why? Because the function we use to divide is monic. The leading coefficient is 1. Okay, the highest degree term is x, and then the leading coefficient is 1. It's monic. We can use division with remainder. Okay, then we can divide my px with some quotient, and then maybe you have some remainder. So if we wanted to show this px is a multiple of x minus 2, Rx has to be 0. By division with remainder, what we know about this remainder here? For example, when you divide 7 by 2, What is the remainder? Must be less than 2, right? Okay, but in this case here, the remainder must be degree less than the degree that you divide with. So the degree of this polynomial is what? 1. The degree of Rx should be 0. Okay, what's the thing with degree 0? Constant. Okay, you can only have constant here. Okay, then we need to argue that why this constant have to be 0. Okay. So since Rx has degree less than 1 or less than the degree of x minus 2, right? Then Rs R must be degree 0. Must be degree 0. Must have degree 0. That is, R is a constant. Okay. Suppose R is not 0. Okay, suppose R is not 0. What happens? Suppose R is not 0. What happened? What happened to phi? You want use phi or not? Yeah, phi. What happened to phi? Phi to px. What is phi to px? It becomes phi on qx times x minus 2 plus r. Right. Okay. Then phi is a homomorphism. Okay, I can split them. Okay, I can split all the term out. It's a homomorphism. Then what? Then phi on x minus 2 is just 0. Okay, so the first part disappear as a product with 0. How about phi r? What is phi r? Phi r is r again. So you just left with r. R is non-zero. But we have a contradiction here. Where's the contradiction? Px is something in the kernel, but we evaluate to something non-zero. So there's a contradiction here. Since Px is in the kernel of phi, since kernel is in phi, by assumption. Okay? Okay now. So meaning what? It cannot be true that R is non-zero. R must be 0. Okay? So if R is 0, then that means that it is a multiple of x minus 2. Okay. So hence, R must be 0 so that Px equals to Qx times x minus 2 is a multiple of x minus 2. Okay, no? Make sense? Repeat where? Above which one? Which part? Oh, suppose now R equals to 0. Okay. So, so let's go back a little bit more. So let's start with this. What's our goal here? Okay, our goal here is we want to show that kernel phi is a subset of x minus 2. Meaning what? For every element is in the kernel phi, we want to show that it is an element in the. We want to show that it's an element of the principal ideal. Okay. To show that something is in the principal ideal, what do you need to show? You need to show that it can be written as some r times the a. What is a here? Is the x minus 2 here. Okay. So what can you do? You can use division with remainder. Right. You can use division with remainder here. So what does division with remainder tells you? It tells you that you can write px equals to some quotient polynomial times x minus 2 plus some remainder. Okay, does this make sense or not? Okay, you should imagine like 7 equals to 3 times 2 plus 1, like that. Okay, and then what about this remainder here? What's about this remainder here? This remainder must be the degree less than the polynomial you started to divide with. Right. Okay, so this remainder here must be less than x minus 2, the degree. Make sense or not? Okay, but this is a degree 1 polynomial here. So your R must be a constant polynomial. Okay, it's just a number. But what number is this? Okay, we need to argue what number is this. Can it be non-zero or not? Okay. If it is 0, then we are done. Right? If it's 0, then that means px equals to qx times x minus 2 is a multiple of x minus 2 in particular. Okay. So here the QR live in where? This QR live in the polynomial ring. Okay. So let me write it better. So this QR live in the polynomial ring. Okay. So yeah. So if R is equal to 0, then we are done because we already write px as a multiple of x minus 2. Let's say R is not equal to 0. Okay, what happened? Then we will get a contradiction here. If R is not equal to 0, then phi of px is not 0 either. But we assume that px is in the kernel of phi. Okay. So it cannot be true that R is non-zero. Okay or not? Okay. About the rest, okay? Happy? Okay. 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 Let's do one more exercise. Maybe we'll take a break from there. So let's define another capital phi from the polynomial ring of xy to RT. Okay, fixing R again. So what's this map here? I need to tell you where the x and y go. Okay, where should x and y go? So let's take x to t squared, y to t cubed. And this means what? If I take any polynomial in terms of x and y, I just evaluate my x as t minus 2 and t cubed. Okay. So we can use the substitution principle to extend the map. Okay. So what's the kernel of this map? Can you guess what's the kernel of this map? The kernel of this map. What's the thing that gets sent to 0 under this map? Yeah. What's the thing that sends to 0 under this map? S cubed minus y squared. Okay. So the kernel of this graph is equals to x cubed minus y squared. Okay, you first look at, so this is the claim. So you first look at what is phi on s cubed minus y squared here. Right. So phi of s cubed is what? Minus phi of y squared is what? Because phi is a homomorphism. Y cubed, so meaning phi to the x to the cube. And then phi y cubed, y squared means phi to the y squared. Okay. But what's phi to the x? To t squared. Okay. So t squared cube. How about phi to the y? T cube. Okay, to the square. So both of them you get t to the power 6. which cancel out. Okay. Of course, you need to prove this claim here, like just now. From the right to left is easy. Okay, because you already know this go to 0. Multiple of them surely go to 0 by the homomorphism. How about this way to this way? You need to use the division with remainder. Okay, you need to use that. This example is done in the book. I also will include in the lecture notes. You can try it out yourself using division remainder. Argue with the remainder. Why the remainder must be 0? Okay. You can see that if you divide with one of them, right? So the degree of the x maybe need to be less than 3. Okay, and then you need to argue why the remainder have to be 0. Okay or not? Sorry? Why this phi function is the homomorphism? This is by the substitution principle. This is very important concept. Why we can do like this? This is the substitution principle. So let me recall. Oh yeah. It's the substitution principle. Here. Okay, it's by this one, by this substitution principle. Okay, so there exists a homomorphism such that if you tell me where x should go, okay, yeah, that's all. If you tell me where should this x go, where the variable should go under this map, then there exists a unique homomorphism. Okay, is this proof here? I prove it here. We didn't do the proof in class, but I show you an example of this proof. Okay. So what's the definition here? So what's the definition? The definition here is very important. Okay. So the definition here is I give you any polynomial. What do you do? You just need to tell me what you do on the ring coefficient and what you do on the variable. So if you know your x have to go to alpha, where should the power of x go? Just go to the power of alpha. This is definition. And then this mesh up with the intuition of substitution. Right? How do you substitute? If I tell you x, substitute at the point A, then your function x squared have to send to where? If x equal to A, so your function x squared have to send to where? A squared. Very well. Okay. So this is definition. So if I know x go to A, all the power of x should go to the power of A by definition. Of course, this is non-trivial. You need to prove that. You need to prove that this definition is actually a homomorphism. Okay, that's why you need to prove the existent part. Okay, you need to check the existent part. So if I define it this way here, why is it a homomorphism? Okay, you need to check. See, all this I check. All this I check. Have you looked at my lecture note yet? Haven't? Please go back and read. I'll put details in the lecture note sometimes. Not sometimes, should be all the time. You have to read. Because in the class, I cannot get everything to details, no time. Right? So in class, I will talk about main point. And then you go back, you have to check the detail. And then if you don't understand second class, you have to come and ask me. This is how my class works. Yeah, no? Yeah, so in class, I talk about points, principle, Okay, go back, you need to work out the detail. Okay, if you cannot work out the detail, you have to come back and then we check together what happened. Does it make sense or not? Okay, so please, every lecture notes, every lecture after lecture, please go back and read the lecture note I put. Okay, they will have all the details there. Should be. If it's not detailed enough, you should ask me. Make sense? Okay. And because this is just one variable case, part B will extend to multi-variable case. Okay, so you tell me where all the variables should go. It also extends to a homomorphism uniquely. Okay, uniquely. Okay. Yeah. Any more question? Guys? Okay. So 3 students that hand out assignment late, not here today. Okay. Let's take a break to 9:06. Okay, let's take some attendance. Venus, yeah, 乐天 like online. 伟哲 yeah, 善娥 yeah, 严科 泽瑞 what other courses you take this semester? Sorry? 总结 what he said. What did you say? I can't hear. Physics or statistics, and then mechanics, and then ODE, and then what was that object? One or two? One. Oh, okay. So which year are you in now? Which year? Second year? First sem? These courses are similar to what they take. No? Which year are you in? Third year. Which sem? Which sem? 总结 can you hear? What sem? Which sem? First sem. Oh, okay. I see. So you are retaking all the courses or what? Yes? Yes, okay. 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 So I mean, if you have difficulty, right, you have to come see me. Okay. Because if you figure out yourself, it's kind of difficult. Yeah. And then I can see from your assignment you are quite struggling. So I hope you can get help. Okay or not? Yeah. Because these courses is not like you sit there for a few days, maybe you can know something because this thing is hard. This thing is hard. Okay, it's not easy. Okay or not? Please come to my office hour if you need help. Okay. Yeah. Yeah. Y square minus x. Equation? You mean y square? Yeah, can because if you have x cubed minus y square, right? Every element is multiple of, so you can build that. How do you build that element? No, 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 no. Huh? Okay, you asked this question, right? So is it true that this is equals to this? Right? What? What do you have multiple? Multiple take who product? Product of who with who? I mean, M like this? You mean is this in the kernel? So you just evaluate this with phi, right? Then what do you get? Phi m times phi of s cubed minus y squared. Now the second thing always go to 0. So 0 times anything is just 0. This is the principal idea. Yeah, this is the principal idea. Yeah. I sometimes I put round bracket, sometimes I put square bracket. It's the same thing. Yeah, yeah. This is the definition here. Yeah, yeah. Yeah. Yeah, yeah, yeah. Yeah. Usually, if I take a singleton, I will put the set bracket. Yeah, yeah. If I just one single thing inside there, I put the set bracket. Yeah. Okay, no. Yeah, it's a principal idea. Yeah. Raven, Siyu not here. I thought Siyu was around yesterday. Ginseng, Ginseng, Xuân Linh, Hải Luận, yeah, Jin Bo, Wang Ying, Xuân, yeah, Yixuan, Ying Qi, yeah, He Yi, He Sik, Xue Yan, yes, Jia Ye, Li Kai, yeah, Yuan Jia, Wen Su, Yi Ding, Yu Wei, yeah, Yan Bo, Tần Ye, So Sing, Lin Jing, Dong Jie, Yi Zhou, yeah, Ling Yu, Liu Xing, yeah, Zheng Chen, Suan Ling, yeah, OK， 鼓励有子谦、何轩、英宁、X、叶、嘉文、嘉文、明修not here. 9 o'clock also never ever arrived. He said 9 o'clock, right? Yeah. Michelle, Ryan, yeah, Ellie, 雪梅，子源。OK， 李凯 ，Are you going okay or not with your typing? 啊，OK 啊，啊，What do you mean by okay? How are you doing or not? 啊？No, I seriously, I just want to ask you, you still want to do or not? 啊啊。所以呢，大家知道，不用紧，你告诉我们有什么。Seng. Hey, is it time's up? Time's up. Time's up, right? Okay. It's good that I saw some of you tell me that you have a study group, right? You have study group. You ask each other assignment question also, which is very good. Okay, which is very good. I have posted up the last assignment already. You can have a look. Okay, I just posted up this morning or yesterday. I forgot. So for this last assignment, right? Please tell your friend. Okay, don't drag this assignment. Please don't drag this assignment. 不要迟交，因为 because this will affect the others feedback， 它会影响到全部人的进度。It will affect your progress because if someone submitted late, I cannot give you the feedback earlier, and I cannot release the solution earlier. Okay, please remind your friend to wait before the deadline. Okay or not? Okay, and then you all have to start it earlier. If you all choose to drag, it will affect your finals. Okay, that's my advice. So that's we have only 3 weeks left. I hope you can put the final booster on this course, finish it with a good ending. And if you don't like pure maths anymore, most probably we won't see each other again. But please put this to a good ending. Okay. Okay. So please put the final 3-week booster before we finish the sem. Yeah. Okay. Hopefully we all work to a good ending. This like a trash. Okay. Yeah. I have a lot of offer a lot of help for you. Most people only come during the near the assignment submission time, so make sure you come and get help. Okay. If you don't want to come and get help, it's really hard, you know. Yeah. It's really hard. Okay, let's continue. Let's continue. So we talk about ideal generated by one element. So we can talk about ideal generated by a few elements. Okay, a few elements. An ideal I, okay, generated by the set of elements A1 up to AN. Okay. So what's this? Okay, if I say I have a set and then I take all the multiple, all the combination of it, what does it call? Okay, so these are the smallest ideal that contains those elements. Okay, so we need to be mathematically workable with this definition, right? So, or more precisely, what is it? Okay, more precisely, what is it? I should be able to write this definition in terms of set notation. Okay, so what are these elements? So, if more precisely, it is the set of all linear combination. Okay, what are the linear combinations here? These are R1 times A1 up to Rn times An. Okay, with coefficients Ri in the ring. Okay, or it is denoted by the round bracket A1 comma up to An. Okay, so this A1 up to An will generate a set, okay, an ideal, which the elements are just linear combination of AI. So this is the definition, right? So when you say is addition multiplication always an ideal or not? It's always a law of composition or not? It's not. You need to check. Okay, you need to check. Similarly, I define this. I said this is an ideal. You need to check. Is this really an ideal or not? Is this set close under addition or not? Is this set close under multiplication by ring element or not? Okay, you need to check. Okay, like how I check the principal ideal just now. You need to check. Okay, we need to check. Can or not? We need to check. Okay, you need to check. So for example, let me see. Let's for example, what kind of possible ideal you can write? So let's look at the integer polymerase over integer, okay, to FP. And then what's this map here? I need to tell you where this polynomial go. Okay, I substitute x with 0. Okay, I evaluate x at 0. Okay, and then mod p. Okay. What's the kernel of this map here? Yeah, what's the kernel of this map? What's the thing you kill in this map here? What's the thing get sent to 0 first? Who say? P, right? First of all, P must get sent to 0. Or any multiple of P. What else? 0 of those go to 0. Yeah, it's a trivial thing have to satisfy by a homomorphism. What else? Sure, x minus p go to 0 because x go to 0. Right. So x should go to 0. So the simplest thing is x and p. Okay, linear combination of them. Correct. Linear combination of them. Is it true? Linear combination of them. X and p. X minus p in particular is a linear combination of x and p, right? Okay. So actually this kernel here is generated by, so the claim, so the kernel here is generated by p and x. Okay. Generated by two things. Yeah, sorry. Sorry. Yeah. Yeah, S squared, S cubed, yeah. Why are they not in the generators? I mean, generators, what does generators do? What does the generators do? Uh, let me think. That should be in there. That should be in there because it is closed under ring. It is closed under ring multiplication, right? But your ring consists of x, right? Make sense or not? What's your ring? Your ring is zx. What is in zx? X is in there. But what does it mean by linear combination of p and x? It means that you can take the ring elements and multiply with your generators. Okay, so you have x squared. Make sense? Yeah. Okay. Okay. So here is the claim. Okay, the kernel of V is px. So you need to prove. Okay, you need to prove why this is true. Okay. One direction is easy because you just evaluate linear combination of p and x. Correct or not? Okay. So let me write out. So the direction px is in the kernel of V is easy. Okay. Why? Because you evaluate linear combinations of p and x under phi. What did I write for phi? Yeah, okay. Makes sense or not? Does it make sense? Does this sentence make sense to you? Okay. And how about the other direction? The direction you also need to use the what? The division remainder, for example. Okay, so let's do the other direction. So how about kernel phi is in the ideal generated by P and X. Okay, how to show this? So of course we need to take an element. Okay, in kernel phi, it means what? It means what? It means that P of F is equal to 0. And then we try and write the fx equals to some polynomial form. Okay, let's write fx as some polynomial. And then phi to f is 0. What can we see from here? What can we see from here? So if I evaluate phi of this f here, what do I get? What do I get? What do I get? I should get 0. Okay. But first you need to look at f0 first, right? So you need to get f0 mod p. Okay. So what is f0 here? This is my definition. Right. So here is the definition, f0 mod p. So what is f0 here? A0, correct? A0 mod p. Okay. This means what? If f is in the kernel of phi, then phi of f x or then a0 has to be equal to 0 mod p. Okay. Then what? A0 mod p equals to what? What does this mean? This means there's this b, okay, there's this b in z such that a0 equals to b times p. Correct. A0 is divisible by p. You know why the second last line here is true? Because fx is in the kernel of phi. I want this to be 0. Okay, so this means that a0 mod p has to be equals to 0 mod p. If a0 is equal to 0 mod p, then a0 equals to bt, multiple of p, because it's divisible by p. Then what? I can start the bp here. So the last term here is multiple of p. The previous term here is multiple of x. So I'm a linear combination of x and p. Okay, I show that everything in the kernel of phi must be a linear combination of p and x. That's enough. Okay. Then and what? Then fx equals to an xn up to a1x plus bp. And you can see that these are the linear combination of x and p. Okay, now. So therefore, or hence, fx is in the ideal generated by p and x. Okay, now. So you can see that everything here should be in zx. And then b is in zx as well because b is in z, generated by x and p. Linear combination of x and p. Yes.
So is this make sense for polynomial ring except from the integer ring or real number ring? Okay.
Uh-huh. What's true? What's the statement is true? I don't know what statement is true. What is true? You didn't say what statement is true. What thing is true for this ring? What is true? You haven't said. I don't know what thing should be true. You haven't said the statement yet. You just say you just change my ring. Then what statement is true? Ah, so does the definition, does the MAT211 make sense if I switch to, for example, polynomial ring over real over complex, something like that, right?
Yeah.
Okay, is it true? I think how to say how to put this.
I can't imagine how
Uh,
the real number. I can't imagine how to use.
I think you cannot. You cannot. But later we will make a things what is called a characteristic P. A characteristic P. And then yeah, you cannot, but you just can do it on the integer. Yeah, you cannot. Yeah, just integer. Because you didn't see what is R mod PR, right?
Yeah.
There's nothing like that, right? Yeah. Yeah. And then maybe you should try where the construction failed. Will the construction fail now? If you want to do what is R mod PR, for example, what is R mod 2R? Will it fail or not? Where does the thing fail? Where does the thing goes wrong? Okay. Let's go on. Okay, let's go on. Proposition. So the only ideal, okay. So let's look at field. Field is a ring. Okay, what's field again? How is field different from ring? Multiplicative inverse for all the non-zero element. Okay, zero is not invertible, but all the non-zero ones should be invertible. Okay, multiplicatively invertible. So the only ideals of a field are the zero ideal and the unit ideal. Okay, and the unit ideal. B, a ring that has exactly two ideal is a field. Okay, these two proposition is very strong. Okay, it tells you when is the ring a field. If you want to go about definition, what do you need to do? You need to go and check whether all the non-zero element has multiplicative inverse or not. But here tells you that look for all the ideal. Okay. If there's only zero ideal and unit ideal in there, then this thing is a ring. So first line, how to prove? Okay, what did I wrote here? Chicken. Okay. The only ideals of a ring are the zero ideal and the unit ideal. So obviously zero ideal is in the ring, in the field, because you just take the zero and then make the ideal. How about unit ideal? Why all the ideal are unit ideal? Why others ideal are unit ideal? You take any element in your field, right? Generate with those elements, right? What did I say just now? What's a unit ideal? Unit mean what? So the unit ideal is a principal ideal generated by what? So if I take any element in the field, I generate the ideal. Do I always get one inside my ideal or not? Any non-zero element, I generate the ideal. Do I always get one? How to generate? You take linear combination, right? You take the multiple with the element inside a ring, right? Do I get one or not? Think about it. Think about it. It should be non-zero. Think about it. Take any non-zero elements, right? Use them to generate the ideal. Can you find one inside there or not? Can you find one? Non-zero element in the field satisfying what property? It is multiplicative. It has a multiplicative inverse. So if you take the multiplicative inverse, multiply with AI, what do you get? One. Don't you get one this way? Right. Okay. So here ideal I, we will see that one is in I. Okay. Because AI inverse times AI equals to 1 and AI inverse is in the field. Let's call our field F. Okay. Make sense or not? Question? Question? Any question? This is supposed to be not hard. So if you have problem, you should ask. Question or not? Should I go on? Okay. If you don't understand this step, right, you haven't familiar with the definition, so I have to recall. So you need to ask so that I know what definition you're not familiar with. Okay. Okay, let's go to the second one. B. A ring that has exactly two ideals is a field. Okay, how to prove this? Sorry, what's these two ideals here? These two ideals here, these first of all, these two ideals. Sorry. Yeah. Yeah, every ring must have zero ideal and unique ideal, correct? Okay, so if you only have two rings, these two ideal must be these two, must be the zero ideal and the unique ideal, right? Because in your ring you must have a zero. Your ring, if it's non-zero ring, then you must have one. Okay. If one is equal to zero, then this is not a field. So in this case here, these two ideal must be zero ideal and zero ideal must be zero ideal and the unique ideal must be the zero ideal. Okay, this is the only one. And the unique ideal. This is the most simple ideal you can form with any ring because your ring must have 0 or 1. If your ring is 1 equal to 0, then it is a 0 ring. If it is 0 ring, then it is not a field. Okay. So if you have two ideals, exactly two, it must be the 0 ideal and unique ideal. Okay. But what? But what? How to prove your ring that has unique ideal and 0 ideal is a field? So can you deduce that one of this is the ring or not? Unique ideal will get everything in your ring. So this unique ideal actually is your ring. Okay. This unique ideal is actually in your ring. So we use that the unique ideal is the ring. Okay. Then what? It means that this ring here is generated by 1. Okay. So let me write down the sum notation so that easier to see what's going on. Yeah. R equals to the principal ideal of 1. So to prove that this is a field, right? What do you need to prove? All the non-zero element here is invertible. Okay, how to prove all the element here is invertible? So I need to take a non-zero element from my ring and then find the inverse for you. Right? Alright, true? True. Hey, too cold like this. Cannot find girlfriend, boyfriend. Too cold already. Okay. Okay. So we want to take any non-zero element R in R. Okay. And we want to show that this R inverse such that R inverse equals to identity, which is 1 in our case, equals to R inverse. Right, to show that R is invertible. Recall definition, R is invertible. I have to find the inverse. But in our ring, is multiplicative, right? So finding R, what did I wrote here? Why I wrote the same thing? So here is okay. So if we can found one equation, because our ring is commutative, okay, R inverse is equals to R inverse R, because our ring is always commutative. Okay. So can we find this or not? Can we find an inverse such that I multiply to this R here, I get identity? Can I do that? Can or not? From this piece of information here. What is this piece of information? What is the ideal generated by one means? So what's the elements? What does the elements look like? Huh? The unique ideal. The principal ideal generated by one. How do I write? R times A. So what's A here? 1. Where these are in my ring. Okay. So this means what? Okay, maybe we change the notation a bit, later clash again. So let's change notation. Change this non-zero one to M. Okay. So meaning what? M is something in the R. Okay. It's something in R. And M can be written as something times 1. Is this enough or not? Is this enough or not? Is this enough? Not enough. Not enough. How? Is this enough to find the inverse or not? Is this enough to find the inverse? Not enough. Oh, how? How to find the inverse? We want to show that there's an inverse. How to find inverse? Yeah, try to think about it. How to find the inverse? How to find the inverse? Huh? If this is non-zero, right? What can we do? We can play a trick. What is the trick here? We can look at the principal ideal generated by M. Okay. But there's exactly only two ideals here. So this M ideal has to be zero, ideal generated by zero, or ideal generated by one. Zero ideal only contains zero, but here contains non-zero M. So this M here must be equals to the ideal generated by one. So what does this mean? So if I take one here, one is also in the ideal generated by M. Okay, so this means we can write one as a multiple of M. So there exists, that is, there exists an R in our ring such that 1 equals to R times M. So you can take your M inverse as your R. Okay, or not? Does it make sense? So I need to find a way, okay, so that I can write 1 as a multiple of M. So so what is this inequality? Equalities here says 1 is a multiple of M. Okay, or not? 1 is living in the ideal generated by M. Does that make sense? Okay, or not? This equation here says what? 1 is a multiple of M. Because 1 equals to something times M. Okay, in the ideal language, it means 1 live in the ideal generated by M. And then how we get this equation here? We consider the ideal generated by M. But just now we said that our ring only have two ideal. One is zero ideal, one is unit ideal. This M is non-zero. So you cannot just have zero here. So it must be the unit ideal. So if these two ideals is equal means what? Everything in here, everything on the left hand side is on the right hand side. Everything on the right hand side is in the left hand side. Okay. In particular, we can see that 1 can be written as a multiple of M. This is what you need. Make sense or not? Does it make sense? Okay. So the R that this ideal give you is exactly the inverse unit. Because it is the thing that multiply to M, you get the identity. Okay. So you can choose your M inverse to be R. Okay. So that okay or not? Yeah. Any question before we take a break? Finish. Any question before we finish? Okay, so I give you the last corollary and then we'll finish. So the last corollary is every homomorphism phi F to R, a field F to a non-zero ring is injective. Okay, so this is a very strong result. Strong result. because every homomorphism from R, this classifies homomorphism from a field. Okay, if you have a homomorphism from a field to a ring, it is always injective. If it is not injective, it is just a zero map because there's only two ideal. Okay, the kernel will be an ideal. So this is the analog to group. In group, what's the kernel of the group homomorphism? Kernel of a group homomorphism is a normal subgroup. Kernel of a ring homomorphism is an ideal. Okay, ideal generalize the kernel. Your kernel must satisfy the ideal property. So, but in the field, you only have two ideal, zero ideal or the unit ideal, the everything. If your kernel is everything, that means your map is zero. You kill everything. So the other option is your kernel must be the zero ideal. If your kernel is the zero ideal, then a ring homomorphism is injective if and only if the kernel is just zero. Okay, so this is about field homomorphism. Okay, any more question? No more question. So in the future in AA2, you study field extension. Why field extension is interesting because of this. You can see that the field is sitting inside a larger field, and then the larger field will be sitting in even larger field when you include more elements inside your field. Okay. So I don't know, but this is the content of AA2. Okay. Field extension. Yeah. I don't know. I don't know yet. Depend on the. Okay, we'll see you next time. Oh, by the way, there's a calculus seminar on Friday. All of you are welcome to come. I'll put out a notice soon, as the time is after our class. Yeah, 6 to 8. I'll put out the notice. Perform, right?